Hello, today we are going to look at something called Bernoulli Trials, which is probability if where we have multiple experiments, multiple trials running over and over again, and those trials are independent of each other. So say if we were rolling a dice a whole bunch of times, we'd be able to use Bernoulli Trials to figure out what the probability of different outcomes would be, or if we were taking cards from a deck and replacing them after each selection, then we would be able to use Bernoulli Trials. But if we were taking cards from a card deck and we didn't replace the card each time, if we didn't put it back in the deck after each experiment, then we couldn't use Bernoulli Trials because the events would not be independent. We'd be changing our total number of cards each time, so they wouldn't be independent. So Bernoulli Trials are where we're doing something repeatedly, an experiment or a trial repeatedly, and the events, the trials, are independent of each other. Those are the kind of key things that often come up with Bernoulli Trials. When can we use them? When we're doing something repeatedly and those things are independent of each other. And really where we have a success or failure outcome as well, where we have either one thing or another would be another constraint of Bernoulli. But let's look at the formula that we've got for Bernoulli Trials. And it's the probability of having or successes, or number of things that we want, out of n trials is going to be n choose or multiplied by the probability of success to the power of the number of successes multiplied by the probability of failure, q, to the power of the number of failures. So that the number of trials minus the number of successes would give us the number of failures. So that's the formula. And again, we are looking for only being able to use this with multiple independent experiments where we have a success or failure type situation. The formula for this is not exactly in the log tables. This formula does effectively appear, but it actually means something slightly different. However, for our purposes, you can go to page 33 in your log tables and you can look for something called the binomial distribution, which for reasons we're not going to get into, to do with the fact we have a success or failure state here, is actually the same formula as the Bernoulli Trials. So the formula is in the book, it's just not called the thing you would be looking for. So we have to know to go to the probability section and then look for binomial distribution formula instead of the Bernoulli Trials formula. But if you get stuck, it is on page 33 in the log tables. Now, let's put this into practice. For a biased or an unfair dice, the probability of getting a 4 is a third. So with a biased or an unfair system, not all of the outcomes are equally likely. That's our meaning of biased or unfair in maths, that we don't have equally probable outcomes for all of our situations. So part 1, find the probability of getting 1 4 in 3 rolls of the dice. So let's go to our formula and let's write down our formula. So P of or successes is going to be n choose or on probability of success to the power of number of successes on probability of failure, power of number of failures. So let's figure out what the different parts of this would be in this case. So what would n be equal to? Well, we're running the experiment 3 times. We roll the dice 3 times. We're looking to have 1 success in those 3 times. We're looking to get 1 4. So or would be one time we need to get a 4 in order to meet our criteria. What's the probability of success? Well, we're told just directly in the question the probability of getting a 4, the thing we're looking for, is going to be a third. And then what's the probability of failure? Well, we know the probability of success plus the probability of failure would cover everything, so that would be adding up to 1. Rearranging that, as we often do, we have 1 minus a third is going to give us the probability of failure is going to be 2/3. So that's how we can find out our different pieces of information. So the probability of getting 1 4 in our 3 rolls, you can say in 3 if you like, is going to be 3 choose 1 3 trials, 1 success, multiplied by the probability of success to the power of 1 on probability of failure, not getting a 4, to the power of 3 minus 1, which we could rewrite as, just tidying it very slightly to make it clearer. We have the number of successes times the number of failures, and then the 3 choose 1 gives us all of the different ways that we could order that situation. So the 3 choose 1 gives us all of the different orders that we could have to this situation. And we're actually going to write that out explicitly now. So when you put this into the calculator, when you use the Bernoulli formula, you're going to get 4/9. So when you use the Bernoulli formula, you're going to get 4/9. To show us where this formula is really coming from, we're going to write it out explicitly, because I've deliberately gone with a fairly small question so that we can write out all of the possible outcomes and see where this choose business is coming from. So probability of getting 1/4. Well, what are the different ways that that could happen? Well, we could, on the first roll, we could get a 4. So that would be a success, and then we'd fail the other 2 times. Or we could fail the first time, succeed in the second time, and fail again in the third time. Or we could fail, and then succeed the third time. And that would be all of the different ways in which we would be able to get 1/4 when we roll the dice 3 times. And we can see that that is effectively going to give us the same result as 3 choose 1. So 3 choose 1 is 3. So this is explicitly listing out all of the possible outcomes, and this multiplying by 3 choose 1 gives us the same number of outcomes. So that's what the choose business is doing in front of our Bernoulli Trials formula. We have our particular setup. So each one of these would be 1/3 by 2/3 by 2/3, 2/3 by 1/3 by 2/3. So each one of these would end up being 1/3 times 2/3 times 2/3, or 1/3 on 2/3 squared. Each one of these situations would multiply out to that probability. And then we have 3 different possible setups that would give us that situation. So that's where the formula is coming from. That's why we have a choose thing going on in front of our probabilities being multiplied together. It gives us all of the different ways that this can happen. Now, that is our little aside as to why the formula is working the way that it is. This is what you actually need to do in the question. This is an aside to show you where this ordering, where this choose business is coming from in the formula. And it's important we have a bit of a feel for that as well. Now, part 2. What's the probability of getting at least 1/4 in 3 rolls? Now, instantly I see this language. I'm thinking, I have seen a special term, at least 1. I know what that means in probability. Probability of at least 1 means the total minus the probability of not getting a 4 at all. This is again a key trick that we have in our probabilities. The probability of getting at least 1/4 equals 1 minus the probability of no 4s. Now there is another way to write this, and I'm going to write it out the longer way for you just now. And here we can see it, the probability of at least 1/4 logically would be the probability of getting 1/4 or 2/4 or 3/4s. Now the issue is, if they'd asked us to do for 10 rolls of the dice, we'd have to do of 1 4, of 2 4, of 3 4, all the way up to getting 10 4s in a row. And that gets extremely long and very likely to make a mistake. Whereas if we can recognize this business here of getting at least 1 4 is 1 minus the probability of no 4s. This is by far the best way to think about it and is necessary for some questions. So it's what we're going to look at. So the probability of at least 1, and here we have it, probability of at least 1 4 is 1 minus probability of no 4s, and we have 3, choose 0 for no successes, which ends up being 3 failures together. So how would we get no 4s? We would fail, fail, and fail, and we'd multiply those together, and we get 2/3 cubed, and we end up with 19 over 27 as our probability. Now, part 3. So what is the probability of getting the third 4 on the 9th throw? Well, to do this, we have to translate this into a problem we can actually deal with. How could that happen, that we would get the third 4 on the 9th throw? Well, that means we have to get a 4 on the 9th throw. And what has to have happened before then is that we must have gotten 2 4s in the preceding 8 throws. So let's write that out. So again, for this situation to occur, we must have gotten 2 4s on the first 8 throws and then a 4 on the 9th throw. So how can we write that out mathematically? That would be equal to, we have to get, in the first 8 throws, we have to get 2 successes. Probability of getting 2 4s in 8 successes, and then multiplied by, and means multiply probability of getting 1 4. So let's write that out. That would be probability of getting 2 4s in 8 would be 8 choose 4 on a third to the 2 on 2/3 to the 8 minus 2, all multiplied by the probability of getting a 4 on the 9th throw, which is just the probability of getting a 4, which would be a third. When we throw all of that into our calculator, we get 1792 all over 19683, which is approximately equal to 0.091. So those are our different steps for our Bernoulli trial, and you can see how